Okay, let's talk about specific heat capacity. And if we're going to do that, we need to understand that specific heat capacity has to do with energy. Energy is measured using these units. We're going to look at both of these units for the sort of things that we do, and later on you'll do mathematical calculations with these. But for now, we need to understand that the more energy something has, we would say it has more joules or more calories. Yes, calories are a type of energy. You might recognize it from nutrition labels. It tells you how much potential energy is inside the molecules of something you eat. So if it has more calories, it has more potential energy in it, which the bodies of most animals store as fat molecules, because if you have extra energy you don't need, then you store it as fat. So that's one of the reasons why eating too much can make you get fat. But as far as what this goes, we need to understand that regardless of the specific definitions, and to be aware of the specific definitions, they're just both basically ways of measuring how much energy something has. Now, if we're going to talk about energy, we need to understand there's a few things that go with it. So temperature is the average kinetic energy in each individual particle, but thermal energy is the total amount of energy in a sample. And we can look at an example of like different amounts of water. This isn't really a good picture because it's hard to see, but you can have situations such as where, here we go, this one, where you can have different amounts of water that have the same energy because the individual particles are vibrating on average about the same amount in, say, a big bucket of water or a small little cup of water at 25 degrees Celsius. So, I mean, separate from what all this says, we have to understand there's a difference between the total amount of energy in all the particles and the average energy per particle. So the total amount of energy in all these particles would be greater than the total amount of energy in all these particles. And that's the reason why this shows this here is if you add the same amount of energy to something that's at the same temperature, because there's so much more, it won't raise the temperature as much as this tiny little amount. That same amount of energy will raise it to be super hot. Okay, again, it has to do with the concept that there is a difference between total thermal energy, we're talking the total amount of all of the particles in there compared to the average energy per particle. Another example might be like boiling water, a little cup of boiling water, and you're taking a bath. Imagine pouring that cup of boiling water into your bath. It might warm it up a bit, but it's not going to do that much. On the other hand, imagine taking a big giant bucket full of boiling water and putting it in your bath. Either way, you're adding water with the same amount of energy, but the total amount of energy in the big bucket is much, much more than the little cup. All right, so that's kind of what this was getting at in spite of the difficult to see picture. Now, aside from that, okay, let's go back here again. We will eventually be talking about the amount of energy it takes to change the temperature of something. And if we're going to do that, we have to consider the amount of substance being heated, as in it's harder to change the temperature of a lot of something compared to if you have just a little bit of something. The size of the temperature change, it's a lot more energy to raise it by 100 degrees than it is by just 1 degree. And the identity of the substance being heated has a big impact on it, because after all, imagine the difference between like a parked car outside next to, and let's say next to your parked car is the lawn. The grass and the car receive the exact same amount of energy, and yet on a warm sunny day, the grass is nice and you can walk on it, roll on it, whatever, it's nice. On the other hand, you get into that car, you better roll the windows down or you're going to die. All right, so it gets at the idea that not all substances react to heat energy being absorbed in quite the same way. Some have a much bigger temperature spike than others under the same circumstances. So this fact, you know, the difference between, say, the grass on a hot sunny day and your car or the hot black pavement has to do with something called specific heat capacity. The amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius is the formal definition of specific heat capacity. And some things, such as a car or black pavement, are going to warm up a lot more on a sunny day than, say, the grass or the ocean. And the reason it has to do with they just inherently resist changes of temperature more in some cases. So every substance has a unique specific heat capacity. It does not depend on the amount of substance, as in like the specific heat capacity of a penny is no different than the specific heat capacity of 1,000,000 pennies. Or I guess the Statue of Liberty is a similar composition to a penny. So the Statue of Liberty and a penny will have roughly similar specific heat capacities because they're made of basically the same stuff. So this is kind of how it works. High specific heat capacity would be like the handle of a frying pan, because when you put the frying pan on a fire, the entire thing absorbs the same amount of energy. The amount of energy absorbed by that super hot cooking surface is the same amount of energy as absorbed by the handle, at least under ideal conditions. What that means is, well, why is it that if you grab the handle, you're fine, and if you grab this, you're going to the hospital? The answer is you have high specific heat capacity. This is highly resistant to temperature change. Here, this plastic of the handle, or wood, or whatever it's made out of. Whereas the metal here has a low specific heat capacity because there's a low capacity to resist heat change. Really what it means is that only a small amount of heat is needed to raise its temperature for low specific heat capacity, so it can't hold very much heat before its temperature goes up. Whereas high specific heat capacity means it can hold a lot of energy before its temperature starts to rise. So each unit of temperature rise requires a lot of energy for high specific heat capacity. Each unit of temperature rise requires only a little bit of energy for low specific heat capacity. But I tell students to remember that high specific heat capacity means high resistance to temperature change. Low specific heat capacity means low resistance to temperature change, and that usually helps. So metals tend to be low specific heat capacity, which is why I say your car, which hopefully is made out of metal, tends to get hot on a hot day, whereas grass or the ocean would be high specific heat capacity because under the same sunshine, receiving the same amount of energy per square meter, they are going to not get nearly as warm. So you're going to want to make sure to fill this diagram in, and this is getting the same idea. High specific heat capacity, a kilogram of water. So if you have the exact same amount of energy as 1 kilogram of aluminum is getting, same amount of energy to each, if you add the same amount, you're going to get a bigger temperature increase for the low specific heat capacity thing and a smaller temperature increase for the high specific heat capacity thing. But it goes the other way around too. If it takes a lot of energy to make the temperature of something go up, then in order for the temperature to go down, it's going to release a lot of energy. In order to make the temperature go down to this, it's not going to release very much energy. Or put a different way, if you release a set amount of energy, then that set amount of energy will make smaller temperature decrease and smaller temperature increase, whereas that same set amount of energy will make a bigger temperature decrease when it's released or a bigger temperature increase when it is absorbed. So that kind of leads into like the sort of things we're going to be talking to regarding this. Okay, specific heat capacity determines how much is absorbed or released during a change in temperature. So we're going to say high specific heat capacity, large amount of energy absorbed or released for each degree of temperature change. Low specific heat capacity, a small amount of energy is absorbed or released for each degree of temperature change. Which is why, like I said, if a frying pan on the stove is absorbing a set amount of energy, that amount of energy for the low specific heat capacity metal is enough to raise it a whole bunch of degrees because each degree only needs a little bit of energy. Whereas the high specific heat capacity handle, it will, because each degree of temperature change requires a lot of energy, it will only go up a smaller number of degrees. So that's kind of what that's all about. Now, practicing that concept, you can look at things and see, like, for example, okay, which would have the greatest temperature increase or decrease, which release the most heat if you did, okay, so it gives you specific situations. So on a test, we would give you this chart, by the way. You don't have to memorize this at all. And you can say, okay, if exposed to 50,000 joules of heat energy, which substance would see the greatest temperature increase and which would see the least temperature increase? And the answer is, remember, high specific heat capacity means high resistance to temperature change. So look at this and think about that. What would it be if you were to have 50,000 joules of heat energy? So equal amount of energy, which one should produce the greatest temperature increase and least temperature increase? The way I go about answering that is I'd look and say, high specific heat capacity means the highest resistance to temperature change. This one has the highest specific heat capacity on the list. So I would say it's going to have the least temperature increase. This one has the lowest specific heat capacity on the list, the 0.13. So this gold is going to have the greatest temperature increase. So that's what this says here. Gold temperature increase most, water increase least in terms of its temperature. So that's how you kind of go about a question like this. So which of these will release the most heat if you cool it to a temperature 100 degrees lower? Which will release the least energy if you cool it to a temperature 100 degrees lower? So same thing, high specific heat capacity. It will it will absorb a lot of energy when its temperature goes up. It will release a lot of energy when temperature goes down. Low specific heat capacity releases only a little when temperature goes down. It will gain only a little in order for its or when you raise the temperature, it only requires a little bit of energy to raise its temperature. So the way I'd answer that is I'd say, okay, so the one, if it's going to go down 100 degrees, the one that's going to take the least energy, or I should say the one that's going to release the least energy is the lowest specific heat capacity. That's going to be gold. And the one that's going to release the most energy is the one at the highest specific heat capacity, which is going to be water. Okay, and that's what it says right here, because like I said, specific heat capacity for every degree, high specific heat capacity is going to release a lot of heat or gain a lot of heat. And for every low specific heat capacity thing, it's going to either gain only a little bit of it, it's only going to gain a little bit of energy in order to raise up its temperature, or to lose only a little bit of energy when it drops down its temperature. All right, so let's look at this. Now, if we want to understand how to do this, we got to think about the thought process behind answering these questions. So 10-gram sample of iron and a 10-gram sample of mercury increase in temperature by 3 degrees Celsius. Which one absorbed more heat energy? So you have to think about something. We're going to do everything in terms of specific heat capacity. So specific heat capacity will tell you what you need to know in order to answer this question. So you're going to choose between iron and mercury by looking at their specific heat capacities. Here's iron. Oops, that's not quite straight. So there's iron, there's mercury. So you can look at those and see that iron has a significantly higher specific heat capacity than mercury. So this is higher specific heat capacity than this one. So you have to think about something. For a given temperature change, which one's going to absorb more heat energy or release more heat energy? If for a set temperature change, does the high specific heat capacity release more energy, or the low specific heat capacity release more energy? Answer that now. Okay, you should have said for a set temperature change, high specific heat capacity will gain or release more energy. So that is going to be iron, and that's why I put iron as my answer here. Now a 10-gram sample of copper and a 10-gram sample of aluminum both released 7,000 joules. Which one got colder? So now, instead of giving a temperature change and asked about energy, we're giving energy and asked about the temperature change. Remember, we're going to look at specific heat capacity. More specifically now, we're going to look at copper, which is this one, and we're going to look at aluminum, which is this one. And then what we're going to do is say, okay, which one had the bigger temperature change? Now you should be able to answer me right now. If you're talking about absorbing or releasing a certain amount of energy, this is just like that frying pan example we talked about. Which one's going to absorb or release, which one's going to have a bigger temperature change? Because they're assuming that they both absorb the same amount of energy, 7,000 joules. Which one's going to have the greater temperature change, the high specific heat capacity or the low specific heat capacity? Answer that now. Okay, hopefully you said greater temperature change will occur in the lower specific heat capacity one. So that means if absorbing heat, the lower specific heat capacity will get hotter. If releasing heat, the lower specific heat capacity one will get colder. That's why I chose the lower specific heat capacity copper as my answer to that. Now let's have you, the viewer, try one out. This number 3 is actually quite similar to number 1. A 10-gram sample of carbon, which I will underline here, and a 10-gram sample of water. When we say water, we assume we mean liquid water. Decrease in temperature by 5 degrees Celsius, which one releases more heat energy? Again, you are going to have to decide, okay, they both had the same temperature change, so which one had more energy released? You're going to have to decide, was it the higher specific heat capacity water or the lower specific heat capacity carbon? Decide that now. Welcome back. If you did so correctly, you chose that the higher specific heat capacity water should be releasing more energy when it cools or gaining more energy when it warms, and should thus have chosen it. Now this one here, a 6-gram sample of ice and a 6-gram sample of aluminum both absorb 1,000 joules. Again, we're looking at temperature We're giving you a certain number of joules, and we're asking about temperature change. So when it asks experiencing a greater temperature change, it's just like here, which one got colder? Okay? In other words, which one had the bigger temperature change? So you look at aluminum and ice. So there's ice, and there's aluminum. You should be able to see that ice has a higher specific heat capacity than aluminum does. So choose now, if they both absorb the same amount of joules, which one is going to have a bigger temperature change? The one with the higher specific heat capacity, aka the ice, or the lower specific heat capacity, aka the aluminum? Choose now. All right, if you're correct, then the one that absorbed, they both absorbed 1,000 joules. The ones that had a greater temperature change would be the one with less resistance to temperature change, which would be lower specific heat capacity, which would be the aluminum. And finally, a 10-gram sample of copper and 20-gram sample of copper both absorb 2,000 joules each. Which has the greater specific heat capacity? Now, ladies and gentlemen, I want you to notice something. This is a trick question. And I'm going to, spoiler alert, the answer is neither, it's the same. Why? Because the specific heat capacity, as mentioned before, does not depend on the amount of substance. Specific capacity is determined by the identity of the substance. So it doesn't matter how much copper you have, 20 grams or 10 grams, it's the exact same specific heat capacity. It's this. No matter how many grams of copper you have, you can have a whole boatload of it, but it's still this for the specific heat capacity. Okay, so make sure not to fall for a question like that. Because although 20 grams of copper can hold more heat energy, specific capacity is energy per gram, which means each gram of this can hold the same amount of energy as each gram of this, and has the same resistance to temperature change, and will react to temperature changes the same way in terms of energy release or gain. All right, so with that said, that should take care of it.